So let's go ahead and work a problem where we're working with a discrete time two-sided signal, and we'll actually find the z-transform of this signal and its corresponding region of convergence. So the signal that we're going to be working with is the discrete time signal x of k equals a negative 1/2 to the k times u of minus k plus 2 times 1/4 to the k u of k. So right off the bat we can see that this is a signal that exists for negative time, and this is a signal that exists for positive time. Combined, this is a discrete time signal that exists over the entire time axis, so it is what we call a two-sided signal. And like I said, we're going to find x of z, the z-transform of this signal, and its region of convergence. So let's start by just writing down the definition of the z-transform. That's the definition of the z-transform. And I can go ahead and break that down into the two pieces. One part is going to be from minus infinity to 0, and it's going to have minus 1/2 to the k, because that's the negative portion of a discrete time signal, plus 2 times the sum. So I've factored out the 2. The 2 is just a constant. It can come out the sum. The sum from k equals 0 to infinity of the positive portion of my signal. And obviously I need to multiply by z to the negative k, because that is in the definition of the z-transform. So far all we've done is plug in our given signal into this definition right here. So let's go ahead and work on this. I'm going to think of that as part 1. In part 2, I really have 2 summations to work through. Let's kind of break those down one at a time. So the first sum, the sum from k equals minus infinity to 0 of a negative 1/2 to the k times z to the minus k. Let's go ahead and think about z to the minus k as z to the minus 1 to the k. So z to the minus 1 is 1 over z. 1 over z to the k I can bring inside with the minus 1/2. So that's what I did right here. I just brought this 1 over z inside this right here and just raised both of them to the k. So this is just the property of exponents here. If we keep working, I'm going to do a little change of variable. I usually like my sums to start at 0 and go to infinity. So if I let n equals negative k, I can go ahead and replace each part of the sum. When k is 0, then n is 0. So that's that part right there. And then when k is minus infinity, n is infinity. So that's that part right there. And then I would have minus 2z to the n. Since k is equal to negative n, I would put a negative n here, but that's the same thing as putting this to the negative 1 to the n. So if we invert that, minus 1 over 2z inverted is a negative 2z. So we've just done a little bit of algebra to simplify that. And now looking at this, we can figure out when does this sum converge. Well, it converges for the magnitude of what's in here less than 1. So I need the magnitude of negative 2 times z to be less than 1, which is the same thing as the magnitude of z being less than 1/2. So first throw away the minus sign. That's a magnitude of 2 times the magnitude of z is less than 1. Divide both sides by magnitude of 2, which is 2, and you end up with magnitude of z being less than 1/2. As long as this is true, we can now just write down what this sum is. So this is just table lookup. It's 1 minus what's ever in here raised to this top limit plus 1, so that is 0. So we have 1 minus 0 on the numerator, divided by 1 minus whatever's ever in here. Minus minus is a plus, so I end up with 1 plus 2z on the denominator. So we've worked out the first part of this problem. We now know what the answer to this part is and for what values of z it converges. Let's go ahead and do part 2. So the second sum was 2 times this summation right here. I'll play the same little game. Z to the negative k is really z to the minus 1 to the k. Z to the minus 1 is 1 over z, so I'll bring the 1 over z inside that first term, and I'll have 1 over 4z raised to the k. We know that this converges as long as magnitude of 1 over 4z is less than 1. Again, multiply both sides and invert, and we end up with magnitude of z is greater than 1/4. So just a little bit of algebra there isolates the magnitude over z, and we end up with magnitude of z greater than 1/4. So for all values of z that satisfy this inequality, we can now go ahead and write down the answer to this sum. It's going to be 2 times 1 minus 0 over 1 minus whatever is inside this sum. So I have 1 minus 1 over 4 z. Do a little bit of algebra. So let's go ahead and multiply top and bottom by z. So I'll end up with a z on the top, a z right here. The z's cancel, and I end up with just 1/4. And the 2 comes through, obviously. So I now know the second sum just fine. 2z over z minus 1/4. And I can go ahead and piece those things together. We now know that x of z is equal to part 1 plus part 2, which is 1 over 1 plus 2z plus 2z over z minus 1/4. For the magnitude of z being bigger than 1/4, that was the inequality that we had here on part 2. And then if we go back to the first slide, the inequality from the first slide said that we needed magnitude of z less than 1/2. So the combined region of convergence is this. So we have found x of z, and we have found the region of convergence. So if we had to sketch this region of convergence in the complex plane, we would sketch the real axis and the imaginary axis. Here is a circle of radius 1/2, a circle of radius 1/4. The points in the z-plane that are bigger than radius 1/4 and bigger than radius 1/2 are the shaded part right here in orange. Actually, to be technically correct, I probably should have drawn my circles to be dashed lines because the inequality does not include the circle 1/4 or include the points that are equal to 1/2. It's only less than 1/2 and greater than 1/4, but I think you get the idea. So that concludes this example of working a z-transform problem where we're trying to find the z-transform of a signal that is infinitely long both to the left and to the right. It's what we call a two-sided signal, and signals like this are always going to have a z-transform region of convergence region in the complex plane that looks like a ring.